Hello everyone, welcome again to EGN 3343 Thermodynamics, and today we're going to continue our discussion on the second law of thermodynamics, and in particular we are going to look into problems that operate under the principle of control volumes, that can be analyzed under the principle of control volumes of the open system devices. And in particular we are going to concentrate on two devices, turbines and compressors. Remember that we had analyzed a set of devices under the first principle and under the reference of open systems devices. We've analyzed turbines, compressors, pumps, nozzles, diffusers, throttles, heat exchangers, but we've only analyzed them from the first principle, first law of thermodynamics point of view. Now we're going to see how the second law of thermodynamics and the concept of entropy affects the operation, not necessarily the operation, affects the analysis of these devices, in particular turbines and compressors. And the second law of thermodynamics can actually be implemented in the analysis of turbines and compressors by the definition of these of the so-called adiabatic efficiency, which is nothing but the deviation from the ideal operation of any of these devices. How would a turbine deviate from its ideal operation, basically the reversible operation, and what kind of power would it produce if it was ideal compared to the power that it actually produces? And in the case of compressors, what kind of power would a compressor require to operate in comparison to what would it require to operate ideally? Okay. Now, in both cases, the efficiency, or the so-called adiabatic efficiency, by the way, some books called it the isentropic efficiency. In both cases, they are defined the same way, but inversely. Because remember that turbines are work-producing devices. Turbines produce positive amount of work. So ideally, they would produce more work than what they would in reality produce. On the other hand, compressors are power consumption devices, so are pumps. Pumps and compressors are the same. The only difference between the two is that compressors operate on uncompressible fluids and pumps operate on incompressible fluids. But both are power consuming devices. So the power is negative. The work is input. The work is done on the system, so it's negative. So they would ideally require less power than they would actually require. So the adiabatic efficiency in both of these cases, the turbines and compressors, is actually defined inversely. So let's see. By the way, when we talk about adiabatic efficiency, we're not talking about a cycle. Remember that the efficiency of a power cycle is always the amount of work, the net amount of work produced divided by the heat input into the system or into the cycle. In the case of turbines and compressors, the adiabatic efficiency, we're just talking about a single process from inlet to outlet. What is the adiabatic efficiency? What is the efficiency of a turbine? What is the ratio of what it actually produces in comparison to what it ideally produces? So in the case of turbines, for example, remember that a basic turbine is a single input, single output, and it's a power producing device, so it produces a positive amount of work or a positive amount of power out of the shaft. The adiabatic efficiency of a turbine is defined as the work that it would produce adiabatically or divided by the work that it would produce isentropically. Well, assuming that the turbine operates adiabatically no matter what. Remember that if it operates adiabatic and reversibly, meaning ideal, it would actually produce more work than what it actually does. So what would be the work that a turbine would produce if it's adiabatic and reversible, as opposed to what it would produce if it were just adiabatic but not reversible? Okay. From the first law of thermo, eliminating Q, knowing that departing from the premise that the turbine is adiabatic, also eliminating changes in potential energy and changes in kinetic energy, the specific amount of work, is equal to the change in entropy, or the negative of the change in entropy from inlet to outlet. Remember that in turbines, the fluid at the inlet has a high amount of entropy. The turbine consumes that entropy, it reduces that entropy of the working fluid, and it uses that to produce work. So the change in entropy of the working fluid in a turbine is negative, and negative times negative will yield a positive amount of work. This is directly from the first law of thermo. Remember, Q minus W is equal to delta H plus delta kinetic energy plus delta potential energy. Now, if we use this from the first law of thermodynamics, we notice that the work produced adiabatically is entropy at point 1 minus entropy at point 2 if the turbine were adiabatic only, and the denominator of the efficiency is the isentropic work is entropy at point 1 minus the entropy at point 2 if the turbine were adiabatic and reversible, meaning isentropic. So obviously the denominator will be larger than the numerator, because the denominator is the isentropic amount of work that this turbine will produce. It's ideally, if there weren't any irreversibilities, if there weren't any friction, if there weren't any losses, hysteresis, everything will be done reversibly. Now, on the other hand, we have compressors and pumps. And remember, compressors and pumps are power-consuming devices. The work is input through the shaft in order to increase the entropy of the working fluid. Okay, they operate exactly opposite to a turbine. Same way in a pump. In a pump, the power is input through a shaft in order to increase the entropy of the working fluid from inlet to outlet. The only difference between the two is that, well, compressors operate on compressible fluids, such as maybe ideal gases, air, hydrogen, so on and so forth. And pumps usually operate on incompressible fluids, liquid water, for example. The first law of thermal for both is identical, it's exactly the same. The work that is inputted is equal to the negative of delta H. Now in this case, because H is increased, the entropy of the working fluid is increased from inlet to outlet in a compressor and on a pump. Delta H is positive. Times the negative sign, it will yield a negative amount of work. And that's obviously what we expect. Work is done on the system, on compressors and pumps. The work is negative. And so is the power, obviously, according to our sign convention. Now, in the case of the pumps, the first law of thermal yields exactly the same. Work is equal to the negative of the change in enthalpy. However, because the fluid is incompressible, this can actually be reduced to the specific volume, which is the same at the inlet and at the outlet. Well, if the fluid is incompressible, the density will not change, and obviously then the specific volume will not change. Remember, the specific volume is the inverse of the density. So we can use this analogy, or basically the definition of enthalpy, as energy plus Vp, or specific volume times pressure. And notice that in a pump, the work is simply the negative of the specific volume at the inlet and at the outlet times the change of pressure between inlet and outlet. Obviously, the change of pressures in a pump between inlet and outlet is positive because the pressure increases, times the specific volume, which is always a positive number, times a negative sign will yield a negative number for the work. Now, in both cases, obviously, the adiabatic efficiency, compressor or pumps, is defined as the isentropic work divided by the adiabatic work. Notice that this is the opposite as in turbines. It's the isentropic work divided by the adiabatic work. Because now, in a compressor or pump, ideally, which is what we have in the numerator, ideally, a compressor will require less work to operate, to increase the entropy of the working fluid. But in reality, in the adiabatic case, in the adiabatic only case, then it will actually require more work. Now these numbers are negatives. Both of these numbers are negative. So in reality, there should be a absolute values bars around them. But because the numerator is negative and the denominator is also negative, obviously the sign cancels out. So basically, Ws is the difference between the entropy at the inlet minus the entropy at the outlet if the compressor were adiabatic and reversible, meaning isentropic, meaning completely ideal. In that case, the work required will be obviously negative, but in magnitude will be less than what it would be if the process were adiabatic but not reversible, so simply adiabatic. So the difference between entropy at the inlet minus entropy at the outlet during a process or through a process that is only adiabatic. Now this number then is always going to be less than 1. The purpose of an efficiency, or the definition of an efficiency, is a number between 0 and 1. So is the efficiency of a full cycle. It is always a number between 0 and 1. It can never be more than 100%, at least in power cycles. Now, for the case of turbines and compressors, obviously it is defined as a number that is always less than 1, less than 100%. You cannot produce more work than the ideal amount of work in the case of turbines. And in the case of compressors, you can never require less work than what is required ideally. Okay, so this is the definition of adiabatic efficiency, and this is how the second law of thermo plays a role in the analysis of these devices. We've analyzed these devices before under the first principle, the first law of thermodynamics, but we've never introduced this concept of the efficiencies, and that's how the second law of thermo and the concept of entropy obviously plays a role in their analysis. Alright, so now let's implement this concept of adiabatic efficiency and the use of the second law of thermodynamics to open system devices, in particular turbines and compressors. In this case, we have a gas turbine. What we call a gas turbine is simply a turbine operating with an ideal gas, in particular operating with air. Air goes into this turbine at 4.5 bar and 550 Kelvin, which is usually the case. High enthalpy content on the inlet, enthalpy is removed from the fluid, and then is transformed into work of the shaft. It enters an insulated turbine, so this turbine is adiabatic, operating at steady state, and exits at 1.5 bars, so we reduce the pressure of the working fluid. Kinetic and potential energy effects are negligible. If the turbine adiabatic efficiency is 85%, let's determine the temperature at the turbine exit, the real temperature, the work developed, the real work, not the ideal work, and we're going to sketch the process line on a TS diagram. So let's see. So we have a turbine which operates with air. The air goes into the inlet at a pressure of 4.5 bar and 550 Kelvin, and it comes out through the outlet at 1.5 bar. That's the only information we have. So we have only enough information at the inlet to determine the entire state, the enthalpy and everything else. At the outlet, we only have one condition, one property, so we don't have enough information. We somehow have to relate information between inlet and outlet. And we know that this turbine has an adiabatic efficiency of 85%, meaning that due to the second law of thermodynamics, there are 15% losses in the process from inlet to outlet. 15% of work that is not going to be developed, basically thermal energy that is not going to be transformed into work due to the efficiency or basically the presence of entropy in the system or in the working fluid. These are the equations we have. The first law of thermodynamics, Q minus W is equal to delta H, delta kinetic energy, and delta potential energy. Notice that we're working on specific mode. We have no mass flow rate, and we have no information about the mass flow rate, or we have no means of calculating it. So we keep everything in specific mode in this particular case. The adiabatic efficiency of a turbine is defined as the adiabatic work divided by the isentropic work, the real divided by the ideal. Okay. Now, for the ideal case, remember, since this is an adiabatic turbine, we basically, ideally, would want this to be perfectly reversible and the adiabatic efficiency to be 100%. And in that case, if we have an adiabatic and reversible process, the change in entropy between inlet and outlet would be equal to 0. Now, if we operate under the constant specific volume model, then we can relate pressure at the inlet and pressure at the outlet to PV to the power K equals to PV to the power K at the outlet. PV to the power K at the inlet equals to P times V to the power K at the outlet. But let's operate under the variable specific heat model and then use tables instead. And in that case, if delta S is equal to 0, then we can make the relationship using the pressures and the PRs. Remember, we've used this in the table. And these PR is just a function of temperature. It's not a pressure. It's a number that is a function of pressure. That is a function of temperature only. That is listed on the ideal gas tables, ordered by pressure. And because we have the pressure at the inlet and the pressure at the outlet, because we have the ratio of pressures, then we can actually make the analogy and use that ratio to relate also the pressure at the inlet and at the outlet through the PRs at the inlet and at the outlet. And if we do so in order to calculate the ideal conditions at the outlet, because ideally the change in entropy from inlet to outlet will be 0, but in reality it won't because there's an adiabatic efficiency. So let's see. So we go to a table, ideal gas, since we're operating under the variable specific heat model. We cannot say that the delta H is equal to Cp delta T. We just go to a table with the temperature and find the enthalpy. At the inlet we have 550 Kelvin, and that will yield an entropy of 554.74, energy 396.86 should we need it for anything, S0, which is that component of the entropy if we need to calculate the change in entropy between inlet and outlet, is 2.31809, and then PR and VR, which only are useful should the process be isentropic. And we're going to use it. We're going to use PR 11.86. So at the inlet, we have 4.5 bar, temperature 550, entropy 554.74, and PR is 11.86. Then we're going to use this, that for an ideal turbine, not only is insulated adiabatic, but it's also reversible. That leads to saying that the change in entropy between inlet and outlet is equal to 0. The fluid should contain the same entropy at the inlet that it does at the outlet. And if that's the case, P2 over P1 is equal to PR2 over PR1. Now PR1 is PR at 550 Celsius, which is, or 550 Kelvin, which is 11.86, and P2 over P1 is 1.5 bar, or divided by 4.5 bar. That yields a PR at the outlet of 3.953. That doesn't mean that the pressure is 3.953. We know that the pressure is 1.5. That means that PR at temperature 2, whatever that is 3.953. That means that we can go back to the table, check this value for PR, and try to see what temperature that corresponds to and what entropy that corresponds to. So that is inputted here in the table of conditions at the outlet. PR is 3.953. Then we go back to the table, look at the column of PR until we find something that is close to 3.953. We see that it doesn't match any number, but we can bracket it between 3.806 and 4.153. So then we can interpolate between these two values, and we know exactly that the temperature will be at the outlet somewhere between 400 and 410, and the entropy will be somewhere between 400.98 and 411.12. So we perform the interpolation. The temperature at the outlet, ideally, because we're assuming all of these under the premise that delta S is equal to 0, so the temperature at point 2, ideal, or isentropic, is somewhere between 400 and 410. So we're interpolating using PR. The value that we found is 3953, which is bracketed between 3.806 and 4.153. That leads to an isentropic temperature of 4.04 or 404.24 Kelvin. And then we can do exactly the same with the entropy. We can interpolate the entropy between the values of 400.98 and 411.12 using the same proportion, knowing that we know the PR and it's bracketed between these two values. And we find the entropy at the outlet, at the isentropic outlet, is 405.29. Now, if we use this in the first law of thermodynamics, knowing that the work is equal to the negative of the delta H, by eliminating Q, eliminating changes in kinetic energy, and eliminating changes in potential energy, then we can find entropy at the outlet is 405.29, entropy at the inlet was 554.74. Obviously, that leads to a negative delta H, but when multiplied by the negative sign, that leads to a positive work. Ideally, this turbine will produce 149.45 kilojoules of work per every kilogram of air that passes through. So that's our conclusion. This is our conclusion from the isentropic point of view, the ideal work that this turbine will produce. Now, because we have the adiabatic efficiency, we know what this turbine would actually do. We'll lose 15% of that. Basically, we can calculate the actual work, or the adiabatic work, as the efficiency of the turbine times the isentropic efficiency of the turbine. So it's 0.85 times 149.45. This turbine will actually produce 127.03 as opposed to 149.45. Okay, so this is the adiabatic efficiency of this turbine. All right. Now, going back to the first law of thermodynamics, again, the work is equal to the change in entropy. The work is equal to the negative of the change in entropy. Now we can use this new work. Notice that it's less than the ideal work, obviously, by 15%. And we can basically calculate the actual entropy at the outlet. actual instead of isentropic, or adiabatic instead of isentropic. So we can solve for H2A, the actual entropy at the outlet, as entropy at the inlet minus the actual work. So it's 554 minus 127, that leads to 427.71, as opposed to, if we go back, as opposed to the value of 405. So ideally, the entropy at the outlet will be 405, but in reality, it's 427. That means that because of entropy, we were not able to subtract all of this entropy that the fluid carried at the inlet. At the inlet, it had 554, and we were only able to subtract some, so that at the outlet it had 427. What do we do with that value of 427? Well, we basically can simply go to the table, look at the column of entropy. Knowing that the entropy at the outlet is 427, we can bracket it between these two values of 421 and 431 and calculate the actual temperature at the outlet. Not the ideal, but the actual temperature at the outlet. Remember, the ideal temperature was 404. Now it's going to be somewhere between 420 and 430. So we interpolate between 420 and 430 using the actual entropy of 427.7, which is bracketed between 421 and 431, and that results in a temperature at the outlet, an actual temperature at the outlet of 426 as opposed to 404. That means that the gas or the air went in to the turbine at 550 and it came out at 426. But had there not been any irreversibilities in the turbine, it would have come out at 404. So we would have been able to take a lot more entropy from the fluid and turn it into power. If we plot this on the PV and TS diagram, this turbine operates under two pressures, 1.5 and 4.5, regardless of whether this is adiabatic or isentropic. Now, the isentropic process between 0.1, which is at 4.5 bar, and 0.2 is perfectly isentropic. The ideal process is perfectly isentropic. Entropy doesn't change. So notice it's a vertical line in the TS diagram. So it goes from 4.5 bar to 1.5 bar vertically to 0.2s. That's 0.2s, the ideal 0.2. And in the PV diagram, this is actually not a straight line, but it's a curved line from pressure 4.5 to pressure 1.5 bar. So it's a steep asymptotic curve. Remember, it's an isentropic process, so it's almost like P times V to the K is equal to a constant. So P is equal to a constant times V to the power K. So it's a steep asymptotic curve to 0.2s. In reality, then 0.1 is going to move to another 0.2, which is to the right of 0.2s in the TS diagram. Okay? And it's always going to be to the right because entropy can only increase in adiabatic processes. It would never be to the left. Entropy can never go down in an adiabatic process. At best, it can stay constant, like in the ideal case. Entropy will stay constant in an adiabatic process if the process is reversible, but due to irreversibilities, the entropy will increase. It will increase, but the pressure of the outlet will still be maintained at 1.5 bar. So in reality, the entropy will increase. We didn't calculate that change in entropy. It wasn't necessary. We were not asked to calculate that change in entropy, but we know that the entropy increased due to the adiabatic efficiency, due to the irreversibilities. So that's 0.2a, the actual point, or the adiabatic 0.2. And in the case of the PV diagram, that would be the case. It will deviate to the right. Well, how do we know it's to the right and not to the left? Well, because the specific volume will increase in the ideal case. Remember that in the actual case, as opposed to the ideal case. Remember that the temperature is larger in the actual case in comparison to the ideal case. The temperature is larger. As you can see, temperature of the actual case is larger than the temperature of the ideal case at the outlet. That will also mean that at the same pressure, the specific volume has to be larger for the actual case in comparison to the ideal case. All right? So this is a typical example of the use of the adiabatic efficiency for a work-producing device, open system, like a turbine. All right, now let's look at another example of the use of the adiabatic efficiency, or the meaning of the adiabatic efficiency for the cases of work-producing devices such as turbines. Now, we have a steady-state turbine. It's insulated, so it's an adiabatic process, and there's some data that is claimed from this turbine, some data that was measured, where it says that the inlet is 100 psi and 500 Fahrenheit, while the outlet pressure is 2 psi. The mass flow rate in this turbine is 30,000 pounds per hour, pounds of steam per hour, that's water vapor. And the power developed in this turbine is 3,800 horsepower. Now, this is data that was collected and measured maybe through a dynamometer. We are told that kinetic and potential energy changes may be neglected, and we are being asked to evaluate this claim. Evaluating this claim basically means, can this turbine possibly produce this much power of 3,800 horsepower? Now, how would we do this? We basically can calculate the ideal work that a turbine like this will produce, the isentropic work that a turbine like this will produce, and then we can compare it to this one. Obviously, this cannot be larger than the ideal work. Ideal work is the maximum possible. That would be the work would the adiabatic efficiency be 100%. So what does evaluate this claim mean? Well, I just said it. Does the claim performance violate the second law of thermodynamics? Meaning, checks for violations. We have to check for violations of the second law may be made in a couple different ways. We can check the ideal power that these turbine will produce and compare it to this claim power, or we can actually use this claim power and calculate the change in entropy and see if indeed the change of entropy is positive or zero at most or best. So we can do this a couple different ways. We can check the power claim against the maximum power that could be produced by a reversible turbine or isentropic, or we can determine the irreversibility by calculating the change in entropy. We can check the outlet entropy for the claim performance against the inlet entropy, and if we find that the change in entropy is negative, well, obviously change in entropy cannot be negative for adiabatic processes. So here's what we have. We have a turbine which has an inlet of 100 psi and 500 Fahrenheit, and if we go to steam tables, water tables, we find that this is a superheated state. I'm not going to show you the table. This is a table of in U.S. customary units, which you can find in any textbook or you can find online. I didn't post U.S. customary units tables online. I only post SI units, which are the ones that you're going to need for the exams. The entropy corresponding to 100 psi, 500 Fahrenheit superheated state is 1279.1 BTU per pound, and the entropy that corresponds to these data is 1.7085 BTU pound degree Rankine. This turbine has 30,000 pounds per hour of steam flowing through it, and it apparently produces a work or power of 3,800 horsepower. The equations we have is that power is obviously mass flow rate times specific work, and the first law of thermodynamics, Q minus W is equal to delta H plus delta kinetic energy plus delta potential energy. Obviously, we'll cancel or neglect heat transfer. This is an adiabatic or insulated turbine. Delta kinetic energy is equal to 0, and then delta potential energy is equal to 0. For an ideal turbine, S2 minus S1 or S2 minus S1 is equal to 0. There's no change in entropy, so we would assume that ideally this will be an isentropic process. So the entropy at the outlet will be equal to the entropy at the inlet, which we already calculated or extracted from a table to be 1.7085. At 2 psi, this entropy is in the wet vapor region. So we go to the table of saturation at 2 psi, which is the outlet pressure, and check for the entropy of saturated liquid and the entropy of saturated fluid, of saturated vapor, SF and SG. And we'll notice that this entropy of state 2 is within those two values. Being within those two values means that the entropy would actually, or state 2 would actually went into saturation. It went inside the saturation dome. So we can calculate the quality of state 2 using this entropy of 1.7085 and the entropy of saturated liquid at 2 psi and the entropy of saturated vapor at 2 psi. And we found that the quality of state 2 ideally would be 0.879, meaning that the steam went from superheated at state 1 to wet vapor in state 2 throughout the isentropic process. This is assuming that the process is isentropic, that the entropy of the inlet is equal to the entropy at the outlet. Then we can use this quality to calculate the enthalpy of state 2 for the isentropic case, for the ideal case. The entropy of saturated liquid for at 2 psi is 94.02, and the entropy of saturated vapor at 2 psi is 1116.12. That's BTU pounds. Using the quality of 0.879, that yields 992.3 BTU pounds of enthalpy at the outlet, should the process be ideal, should the process be isentropic. Then we can calculate the ideal specific work. Remember that work is equal to minus the change in enthalpy, minus delta H. It's 992.3 minus 1279.1. That yields 286.8 BTU of energy per every pound of air or of steam that passes through this turbine, ideally. Then we can multiply that by times the mass flow rate of 30,000 pounds per hour, and we'll find so many BTU per hour. That's units of power. We can transform BTU hour to horsepower. 1 horsepower has 2,545 BTU per hour. That is just a unit conversion. And then we find that the work, ideally, the work that this turbine will produce is 3,380 horsepower. Well, if we compare that to the power that was claimed by this turbine, by whoever measured the power on this turbine, which is 3,800, that would be impossible. The claimed data of 3,800 horsepower is impossible because it's larger than the maximum power that this turbine can possibly produce, which is 3,380. So, this turbine violates the second law of thermo. This device cannot produce more than the isentropic production of power. So, since the claimed power, 3,800, is greater than the maximum possible power for an adiabatic turbine, the reversible power, the claim cannot be valid. This is incorrect. We can do this a slightly different way. We can check for the second law of thermodynamics violation by looking at the actual change in entropy. We can calculate the enthalpy at the outlet by using the power. Remember that work is equal to minus delta H. Power divided by mass flow rate is equal to work, and that way we can calculate the enthalpy at the outlet. Knowing that the enthalpy at the inlet at 100 psi and 500 Fahrenheit is 1279.1. The power that was given to us is 3,800 horsepower. We multiply that by 2,545 to turn that into BTU hour, not BTUF, it should be BTU hour per every horsepower. And we divide by 30,000 pounds per hour. That's the mass flow rate. Okay, this will lead to an enthalpy at the outlet of 956.7. That would be the enthalpy of state 2. Now we have pressure of state 2, which is 2 psi, and the enthalpy of state 2, which is 956.7. With that data, we can go to the table. We can calculate a quality again, and we find that the quality using this value of enthalpy is 0.844. And with that quality, then we can calculate the entropy of state 2. Not the adiabatic, not the isentropic enthalpy or entropy, but the entropy that would correspond to the state 2 should this turbine produce 3,800 horsepower of power. And that would be 1.6477 BTU pound degree Rankine. That will be the entropy of state 2 using this new quality. Remember that what we're trying to do here is to validate this problem, whether this data is correct, and we're using the methodology of calculating the delta S, calculating the change in entropy. Now we know the entropy of state 1 is 1.7085. That's the entropy that corresponds to 100 psi and 500 Fahrenheit. If we subtract this entropy we found from the entropy of the inlet, we find that the change in entropy between 1 and 2 is minus 0.0608. That makes the whole process impossible because entropy can never go down in an adiabatic process. Remember that this turbine is insulated. We've eliminated Q from the first law of thermodynamics. The only way that the entropy can go in an adiabatic process is up. or it can stay constant at best for reversible processes. So basically, since it is impossible for entropy to decrease in an adiabatic process, the claimed performance is not valid. So we just demonstrated through another method that the data that was given to us was invalid. Okay, it's flawed. All right, now let's look at an example where we have a compressor now. So it's a power-consuming device. And in the case of a compressor, remember the adiabatic efficiency is defined inversely. Is the ideal work divided by the adiabatic work, because ideally a compressor will require less work than what it does in actuality. So that keeps that ratio less than 1 for the efficiency. This is an air compressor. It enters an insulated compressor operating in steady state. It enters at 1.05 bar and 23 Celsius. That's basically atmospheric conditions. So atmospheric pressure, atmospheric temperature, with a mass flow rate of 1.8 kilograms per second and exits at 2.9 bars. So the compressor obviously increases the pressure of the working fluid, increases the temperature of the working fluid, and increases the enthalpy. And in order to do that, it receives power from an external source. We can neglect kinetic and potential energy effects, and we are asked to determine the minimum theoretical power input required and the corresponding exit temperature. So will be minimum theoretical means the ideal, the isentropic power in kilowatts. We have the mass flow rate, so we can actually calculate power. And we're told that if the adiabatic efficiency of the compressor is 80%, we are to determine the actual power input requirement and the corresponding exit temperature. So let's see. This is an air compressor that uses 1.8 kilograms per second of air. It has an adiabatic efficiency of 0.8. At the inlet, we have 1.05 bar of pressure and 23 Celsius, or 296 Kelvin of temperature. And at the outlet, the pressure raises to 2.9 bar. So we have enough information at the inlet to determine whatever we want in terms of enthalpies and entropies and so on. But at the outlet, we only have one thing. So we have to tie up the inlet to the outlet. The way we tie this up is using the fact that ideally, this will be an isentropic process. Ideally, would the compressor be not only adiabatic but also reversible, the change in entropy will be 0. So the equations we have is that according to the first law of thermo, Q minus W is equal to delta H plus delta kinetic energy plus delta potential energy. We're going to neglect the heat because this is an adiabatic compressor. Kinetic energy and potential energy will also be neglected. So basically the work is equal to minus delta H. The adiabatic efficiency of a compressor is the ideal work divided by the actual work. It's the other way around is in a turbine. And if the delta S is equal to 0, in the ideal situation where it's not only adiabatic but also reversible, the change in entropy is equal to 0. And in that case, then we can relate the two pressures, inlet and outlet, through PR2 and PR1, which are only functions of temperature. So we could also do this with the volumes, but we only have information about the pressures at the inlet and at the outlet. So it's obviously beneficial to use the pressure relationship. Remember that PR2 and PR1 are values that are found in tables as a function of temperature that we can use to relate pressure and temperature at inlet and outlet state. And they only are useful or are meaningful should the change in entropy be equal to 0. We can use this if we use the variable specific heat model, but if we use the constant specific heat model, then we can always say that P2 times V2 to the K is equal to P1 times V1 to the power of K, K being the ratio of specific heats. We are going to neglect heat, kinetic energy, and potential energy. Now for the minimum work input, which is part A of the problem, the compressor would be isentropic. At the inlet, we have 296 Kelvin. We can calculate the enthalpy, the energy, S0, PR, and VR. Obviously, the only things we're going to need is enthalpy and PR. So we're going to be interpolating between 295 and 300 because the temperature at the inlet is 296. So using that information, interpolating between 295 and 300 at a temperature of 296, we find that the enthalpy is 296.17 and PR at the inlet is 1.3226. In the ideal case where the process is isentropic, entropy doesn't change, then we can relate PR1, PR2 to P1 and P2. So we can solve for PR2 as PR1 times P2 over P1. And then we can find that PR2 is 3.6530. That doesn't mean anything, but we know that this value is a function of temperature only or exclusively. And we can go back to the table, look for a PR value of 3.6530, and see what temperature and what enthalpy that corresponds to. And that would be the temperature and enthalpy for the isentropic case, because obviously we're assuming that this PR2 applies to the isentropic case. So 3.653. We go to the table, we find a PR at 3.653. Obviously, it doesn't exist, so we have to bracket it between these two values and interpolate. The ideal temperature would be somewhere between 390 and 400, and the ideal enthalpy would be somewhere between 390.88 and 400.98. The ideal enthalpy. Interpolating, we find that the ideal or isentropic temperature is 395.3, and the ideal or isentropic enthalpy is, after interpolation, 396.17. So we can use now the enthalpy that we calculated at the inlet at 296 Kelvin and the enthalpy that we just calculated for the ideal case at the outlet, subtract the two, and find the ideal work. The ideal work in this compressor is minus 100 kilojoules per kilogram. Obviously negative, because compressors are power consuming devices. And we can multiply that by the mass flow rate, kilograms per second, and obtain kilojoules over second, which is kilowatts. So ideally, this compressor will require 180 kilowatts of power to be input to it in order for it to operate, in order for it to raise the pressure of 1.8 kilograms per second of air from 1.05 bar to 2.9 bar. It would require 180 kilowatts. Negative, obviously, because it's power input. But that's the ideal situation. Now, in reality, there is an adiabatic efficiency. The actual compressor has an adiabatic efficiency of 0.8. The adiabatic efficiency of a compressor is defined as ideal power over actual power. Because these are power inputs, then the efficiency of a compressor is defined inversely. So the adiabatic or actual power is the ideal or isentropic efficiency or isentropic power divided by the adiabatic efficiency of the compressor. So it's 180 divided by 0.8. That's minus 225 kilowatts. That's the actual power that this compressor will require. So ideally, this compressor requires 180 kilowatts of power to be sent through the shaft, maybe by an internal combustion engine we used externally to power the compressor. 180 kilowatts is something like 220 horsepower or 230 horsepower. But in reality, in order to accomplish this raise in pressure of the air, we need 225 kilowatts, which is more like 300 horsepower. So we need a 300 horsepower engine in order to raise the pressure of these 1.8 kilograms of air per second to 2.9 bars. Now, this difference is basically because of irreversibilities, because the compressor is not perfect, because there are irreversibilities in the process. Then we can use this power to calculate the actual exit enthalpy so that we can calculate the actual temperature. Now, this power can be divided back by the mass flow rate to calculate the specific work in the compressor. And then we can use the first law of thermo that says that work is equal to minus delta H, and we can calculate the H at the outlet. The actual H at the outlet is given by the H at the inlet, 296.17, minus the specific work, but in this case the actual specific work, 225 divided by 1.8. That yields an actual enthalpy at the outlet of 421.17 kilojoules per kilogram. 121.17. Then we can use that value, go to the table, 421.17, and we can see that it's very close to this value. We could interpolate between 411.12 and 421.27, but it's very close to this one. We'll find a value that is very close to 420 for the temperature, maybe 419.99. So we don't need to interpolate, really. We can say that it's very close to 420, so we just say that the actual temperature at the outlet is 420 Kelvin. as opposed to what we had found before, the adiabatic temperature of 395. So the temperature goes from 296 ideally to 395.3, but in reality it goes from 296 to 420. If we plot this in PV and TS diagrams, notice that in the PV diagram we're going to be the compressor is going to go from 1.05 bar to 2.9 bar, regardless of whether it does so adiabatically or isentropically, ideally or in actuality. And it's also going to go from 1.5 bar to 2.9 bar in the TS diagram. But in the TS diagram, these two pressure lines are growing exponential lines. So it goes from 0.1 to 0.2. When it does so isentropically or ideally in the reversible case, it does so perfectly vertical because the entropy doesn't change. For the case of ideal change for ideal process. So that's 0.2s. 0.2s in this compressor is from 0.1 to 0.2s. Remember, this is a steep asymptotic curve. That's what an isentropic line would look like in a PV diagram. So that's 0.2s. Where's 0.2? The actual 0.2 would be to the right at the same pressure, 2.9 bar. It would be to the right because entropy can only grow in a process, whether it is a power producing process or a power consuming process. Entropy in an adiabatic process can only grow. So that would be, and the process line 1 to 2a, and in the PV diagram this will be the process line 1 to 2a. It will grow to a slightly larger volume because the actual temperature is actually larger than the ideal temperature. The ideal temperature of the outlet was 395. The actual temperature of the outlet is 420, as you can see here. And if you have a larger temperature at the same pressure, that will yield a larger volume. That's why we find that the actual curve is actually steeper than the ideal curve. So this is it for today. This actually completes the discussion on the second law of thermodynamics. We've actually enunciated the second law of thermodynamics as a set of statements and corollaries. We've actually put equations and formulas to the second law of thermodynamics, such as the efficiency of Carnot, and stated that that's the maximum possible efficiency that a power cycle or heat engine can achieve. We then define the concept of entropy, which is a mathematical artifice, which is a mathematical tool to measure the strength of the irreversibility in a process. And we used it to our advantage to make some calculations in closed system problems and open system problems as the ones we did today. In the case of open system problems, we use that concept of entropy to define the so-called adiabatic efficiency for turbines and adiabatic efficiencies for compressors. So, as I said, this concludes the discussion on the second law of thermodynamics. That doesn't mean that we are not going to be using the second law of thermodynamics from this point on. From this point on, we are going to be discussing cycles, power cycles and refrigeration cycles and heat pump cycles. And in all these cases, the second law of thermodynamics, as well as the first law of thermodynamics, will be something that must be used in order to analyze these problems. So thank you for your attention, and I'll see you next time.